didn't save it. I don't know why. Okay. Now, before we get started on today's class, let's review where we've been and what we still need to do. Now, I'm behind. I was trying after our last class I had to develop a lab for chapter 23, and I got it mostly developed, okay, but I didn't have it typed, and that's a slow process for me. So I tried like crazy to get it typed before we left town on Friday morning, but I didn't get it done. So you do not have the lab out there, and I don't think I got the test out there for you either. Apologize on both counts because we're going to stop at 4:15 today to do the lab, but I don't have it out there for you. So y'all are going to have to write down your answers to the lab, and then I'll get the form, and you can either send them to me on the piece of paper or you can fill them in on the form when I send you the form. But that'll be sometime later this evening after 6:15, because I've still got I'm working on a test for my Cal 2 class that I didn't finish typing that either, didn't finish putting it together, and this one I didn't finish typing. So and then I didn't finish getting your other test loaded. I have to go back and redo and undo. Now, someone tell me, did I get the test out there or not? I know I worked on it, but I don't remember. No, I don't think I did. I don't think. Okay, so I've got those three things to do at the end of the day today. So it's going to be a while before I get all three done. But we will do the lab for chapter 23. Now you'll see everything that I'm doing. It'll be recording, hopefully, because the recorder is going. The last class wouldn't save it, but hopefully this class it will. And then when I get you the form, you can either fill it in or you can send me just your answers as you write them down, whichever way works best for you. And then the test will be out there sometime this evening too. So lots to do, miles to go before I sleep tonight. So I'll try to get everything done as much as possible by then. All right, any questions? So let's see. We're going to continue in chapter 4 today from now until about 4:15. I don't have Valerie here yet to keep time for me, so someone watch out for time for me. And then we'll stop there, do the lab for chapter 23, and then next time if we don't finish 24 today, which I doubt if we will finish chapter 24, and I think we'll have plenty of time then to get the lab. I've got that lab already typed up. I just have to put it out there in Blackboard for you. It's not there yet. And then I've got to get the test into a form that I can get it to you as well. All right, and here comes David. So let me get David in here. Okay. All right. David, I hope you're here now. I was just telling everybody else, Zoom has been messing up today. It messed up in the middle of my last class and just cut off right in the middle, and I had to get everybody back again. And then when I tried to get this class started, it just sat there saying it was connecting, 3 dots, and just sitting there, not connecting. So I had to shut it down, pull it back up. It still did the same thing. I went down again. I checked my internet. Everything was good. I pulled it back up again, and then I started trying to, in between I was loading your files. I was doing everything I could think of to do, and ultimately it lost, my Screencast-O-Matic lost my last class, which was frustrating. But finally Zoom came up for this class, at least 6 minutes late. You know, I'd been sitting here working on it for 6 minutes, and finally it came up. So we'll go on chapter 24 today until 4:15. Then we'll go and do the lab for chapter 23. I don't have the questions for you out there, but I'll walk you through how to do it, and it'll be recorded hopefully on Screencast-O-Matic, and it'll be out there on Blackboard, YouTube video that you can access through Blackboard. But I'll try to get all that done this evening. Then when I do get your form ready, you can either copy your information onto the form, or you can just send me the information as you're doing the lab today. Hopefully when we do it, it'll make more sense of what it sounds like it's making now. So, any questions before we get started today? And I'll put your chapter 23 test out there after I get the lab out there, and then on Wednesday we'll finish chapter 24, do chapter 24 lab. I'll give you chapter 24 test, and I'll give you the final exam. I know it's a lot, but it's not going to take you that long to do either the lab or the test or the final. They are all fairly short. So here's the schedule. I think I went over this last time. We have to have grades in, I think, I'm going to check on this, but I think we have to have grades in by noon next Monday, 1 week from today. So that means, please folks, if you haven't done your research paper, and sadly, I think in fact, I'm not even sure I've gotten a single research paper in from this class. Unless you send it in this weekend, I don't have it, okay? You did. Okay, when? Yes. Okay, last night. Okay. I was in Georgia last night and did not have good internet service, so I couldn't check it then. I couldn't have printed it even if I had internet service. So if you send it to me anytime after, well, Thursday evening, I haven't printed it yet. I will be printing them, so thanks for sending those. So, talk about miles to go before I sleep. I've got to finish the Cal 2 test. Oh, here comes somebody. Oh, Scott. Scott's coming in. So let me get Scott here. And go over a few of these things again. Or we'll just stop going over them and just get back to the class. But when I finally let y'all go, whatever time it is today, I've got to finish my Cal 2 test. I've got to finish typing your lab for chapter 23. I've got to get your chapter 23 test into a format I can put out there on Blackboard. I have it done, but I always have to clean it up. It's always a mess. The test bank does not communicate well with Word, and Word in that format doesn't communicate well with Blackboard. So I have to do a lot of massaging to get things to work there. So I'll get those done hopefully tonight, okay? And in class we're going to work on chapter 24 until at 4:15. 4:15 we'll do the lab for chapter 23, even though you don't have the form. So you'll need to be writing down the stuff as I tell you about it, and you'll see it all. I'm recording it, everything will be there, and then you can either turn whatever you write down into me, or when I send you the form you can transcribe it onto the form. That's up to you, okay? I'll take it either way, okay, because it's my bad the form's not done, but I just did not have time to get it done, okay? So after all that, then on Wednesday we'll finish chapter 24. We'll do the chapter 24 lab. That's going to be very straightforward, not nearly as involved as this one is, and I'll give you the chapter 24 test. Hopefully that will be already prepared, because I've still got to do all the stuff for it, and I'll give you the final exam, and that I know is already in a good format that I can just sit. Well, no, I don't know for that for sure. I'm going to have to check on that one as well. Probably have to do a PDF on that one. Okay, so anyway, all that will be done, and then here's what I was saying about the time the last couple people came in. I have to have grades in by noon next Monday, 1 week from today. So that means I'll give you the last of everything on Wednesday. So try to get as much into me. Okay, research papers, I'd love to have them in today. If you can get them to me today, please do. If not, get them to me tomorrow. If not, please get them to me by Wednesday. Okay, technically they were due today. Okay, all of your old tests and labs, please get those to me. Now some of you, like we said, I was away from internet. I mean, not able to print a thing from Friday morning until this morning. So I haven't been able to check internet at all to see what you sent me and whether I can print it or not. I wasn't anywhere where I even had a printer over the weekend. So after I finish the Calculus 2 test, after I finish your lab, after I finish working on getting your test into a format that I can send to you, then I'll start printing the stuff that came in over the weekend, and I'm sure it's going to be voluminous. Okay, and then I'll get back to grading. I got a bunch of your stuff graded over the weekend. I didn't get finished. I've got finished everything that was turned in by Thursday, up to chapter 19 test. I've got this much left to grade. I got at least that much graded over the weekend. I've got that much, and then I'll probably have to print more than that. So it's going to be a busy week. But get to me everything you can as soon as you can. Don't wait and turn it all in at once. As soon as you finish something, get it to me. And today, tomorrow, Wednesday, Thursday, Friday, Saturday, try to get me everything in by Sunday. Sooner than Sunday if you can, but get everything, because noon on Monday, I can't be grading papers Monday morning. I've got to be putting grades in Blackboard, and not just on Blackboard, on the system Monday morning. I can't be grading papers. So if you don't have something to me by Sunday evening, you're probably going to get an incomplete. Then as soon as I have a chance to get the stuff graded, then I'll be able to change your incomplete to a letter grade. So please get me stuff the soonest you possibly can. Okay? All right, here's Valerie. Okay, my timekeeper is coming in. Okay. So, all right. I'll wait and go over the rest of this again when we take our break. Any questions before we get started on chapter 24? Oh, here's Bridget. Good deal. I didn't realize it, but I was advising Bridget's sister Thursday. That's not her fault, but it was one of the reasons I couldn't get all the typing done I needed to from, well, all last week. My advising schedule was filled to the gill. Okay. All right. So for those who have just come in, we're in chapter 24, Earth's Waters, and we're on surface water, and in the big book, this is on page 610. If you have a smaller book, it's on 24-5, the 5th page in chapter 24. Okay. Now, since several people have come in since I said it, I'll try to make this quick. Sorry, you folks have heard it 3 or 4 times now. Please, folks, get me, if you haven't already submitted your research papers, get me your research papers today if possible. Okay? Number 2, all your old labs and tests. Please get them to me. If you haven't already turned them in, please get them to me. Now, don't go by Blackboard. Okay, I don't have all the grades in Blackboard, but if you've sent me something and I've acknowledged that by responding to you that I printed it, don't send it to me again. I've got it. I've probably got it graded, okay, but don't resend it, because then I'll be printing stuff 3 or 4 times. I don't have time to do that. So please, if I've already acknowledged its receipt, don't send it again. Say that again. Did someone say something to me, or was that just a microphone came on by mistake? Roy, was that your microphone? Okay, I don't know. All right, anyway, so please get me the stuff that you're behind. Now, I'm behind too. I'm behind in grading, obviously, but I'm also behind I've got a Calculus 2 test to finish, typing up and getting to students. Well, hopefully I don't have to type it, just getting it to the students. I've got your lab that I've put together, but I don't have it finished typing. I have it all worked out, and I started typing it, but like I said, I ran out of time on Thursday because of advising and other things. Okay? Then your test, it's done, but I can't swear it's in a form I can send you yet. When it comes out of the test bank, it never goes over well. I have to remove a bunch of junk that it puts in there before I can send it to you through Blackboard. I've tried and it just doesn't work unless I clean it up. So I've got to clean up your chapter 3 test. Okay, so at 4:15, Valerie, okay, we'll be stopping chapter 24 and starting to do that lab that you don't have a copy yet. And then when we finish that, I'll be sending you, when I can get it to you, your lab and your test for chapter 23. Okay, then on Wednesday, we'll finish chapter 24, and we won't have that much more to go. We'll have the lab for 24, and then I'll send you the test for 24, and I'll send you the final exam. Okay, now that's Wednesday evening. You'll get those 3 documents: the lab for 24, the test for 24, and the final exam. Final exam is going to be the shortest thing you do. I mean, I think you can probably finish it in 15 or 20 minutes. So it's not going to be that bad. So don't get panicky that you got that much coming in. That's going to be pretty easy. Okay, now, and we'll go through the lab together if you need to, whatever. Okay, now, I'll need everything turned in as soon as you can get it to me. Wednesday would be great. Thursday would be wonderful. Friday would be okay. Saturday's all right, but please get everything to me by Sunday. And get it to me sooner. If you finish something sooner, get it to me sooner. Don't wait and send me 15 documents on Sunday, okay? That's going to not give me time to get everything graded. So get me stuff as soon as you can. All right. Any questions before we get started in chapter 24? Yeah, at 4:15 we'll stop 24 and start the lab for 23. Thank you. All right. So we left off at surface water. And for those who missed last time, we started chapter 24, which talked about water on Earth. We found out that most of the water on Earth, of course, is salt water. I mean, the vast majority is salt water, ocean water, salty. Like 97 to 98% is salt water. That 2 to 3% that's fresh water, we talked a little bit about that as well. We talked about water quality a little bit at the top of page 609. And we're ready to start in 610. In 610 we talk about surface water. Now, backing up just a bit, fresh water is divided into 2 pieces. Actually a little more than 2, but mostly. Surface water and underground water. Now surface water, believe it or not, is just about the smallest that we got. Only thing less than that is the amount in the air, which is just water vapor, which isn't very much. So surface water is not a huge percentage, but it's mostly what we see. And a lot of what we use is surface water. Okay? So that's why we focus on that next. Then we'll talk about groundwater. That's the next section. So surface water is collectively all the water, and this is mostly, and they're talking about fresh water here, in all your streams, in all your ponds, in all your lakes, in all your rivers, in all your reservoirs, everything that's fresh water that's on the surface of the earth. Not underneath, but on the surface of the earth. That's what we mean by surface water. Okay? Now, where is it located? Well, there's a term here. It's called, oh, here comes Capri. Good deal. Capri's coming in. Okay, the top part of the alphabet has come in really, really strong. The middle part is almost vacant. I think Caitlin's holding that up all by herself. And then the bottom part of the alphabet just has 3 people holding that up. So come on, folks, get here. Okay. So the concept here for surface water is where, okay, fresh water comes from the sky. It comes from rainfall, precipitation. It falls down to earth. When it gets to earth, then it either soaks into the earth, we'll talk about that next, that's called groundwater, or it flows on the surface. In these streams, lakes, ponds, rivers, that kind of stuff. I don't know why. Someone just sent me a chat. Does anyone know who that was? Let me see if I can. Oh, it was. And who's me? Who? Capri. Okay, great. Glad you're in here. I won't go to the chat then. Okay. It just popped up, so you got here before it did. Okay. So this water that lands on the earth and doesn't get soak into the earth, it winds up in a stream, in a river, in a lake, something. And what it winds up in an area that's called a watershed. Now, sort of a strange term, watershed. The land area that's drained by a stream or streams or rivers or whatever. The land area that's drained by a single stream or a system of streams or a system of rivers and streams. Okay? Now, if you have two adjacent watersheds, they're separated by something called a divide. A divide is an area of a little bit higher elevation. I'll just give you an example. I don't know how many of you would have ever been on the Bessemer campus, but if you were, when I left the Bessemer campus and drove down the Bessemer Superhighway, actually north on that, northeast sort of, heading toward Birmingham, I didn't drive on it very long, but leaving Bessemer Bessemer campus of Lawson State, not too far there was a hill. I went up a hill. At the top of that hill, I could see the entire city of Birmingham. That had to be a divide because that was the highest point on either side. So water that fell on one side was going toward Bessemer. The water that fell on the other side was going to go toward, well, wait, I'm sorry. It was before I got to the city of Bessemer. So water that fell on one side was heading toward McAdory, and the water that fell on the other side was going toward Bessemer. Okay, that was a divide. It's a large. It's the area. It's really a line or a curve that separates two different watersheds. Now, different watersheds pile up and go into bigger watersheds, like a single stream will go into a bigger stream. That bigger stream will go into a bigger one. And finally, that stream goes into a river. That river will form a watershed with all those streams, okay? All those watersheds. Well, then several rivers will combine and you form even a larger watershed. Okay, so your biggest watersheds are separated in the U.S. especially by though in every continent, by what we call a continental divide. It separates the watersheds that drain on one side of a continent to those that drain to the other side. And this is a little bit surprising at times, but here is the figure that's on your page 24-5 or page 610. Here is the figure. I thought it was the figure that showed this. It won't advance. There it is. Okay, this is the figure that's on your page. Now, in my book, the Mississippi River watershed is green. This one's sort of grayish. Okay, but these are the three largest watersheds in the U.S. And guess who's number one? Okay, big old Mississippi River. Now, it's not just the Mississippi. Okay. There's the Missouri River that comes, well, it goes through Missouri, of course, and heads on up. Where it comes into the Mississippi is at St. Louis, okay? St. Louis is right about there. The Missouri River basically comes across somewhere here, and it's fed by many other rivers. And these rivers all flow into the Mississippi. Over here you have the Ohio River coming in. You have the Tennessee River coming in. You have all kinds of rivers. I think this is the Red River coming in. You have all these rivers coming in to the Mississippi. So the biggest watershed here is the Mississippi River watershed. Okay. Now, on this side, what separates, and by the way, all the water from everywhere you see in this gray area is going to wind up in the Mississippi River somewhere down here, and it flows into the Gulf of Mexico when the Mississippi dumps there. Okay? Now, and it will wind up in the Atlantic. Over here, the Columbia River watershed, and several other rivers contribute here. The Snake River comes in here. Other rivers come in and go into the Columbia River. That goes into the Pacific. That's somewhat, I think it's around Bremerton, Washington, maybe. That actually it may not be far from Seattle. Maybe it's in Seattle. Okay. And also, though, there's another divide here, and the waters south of the Columbia River watershed, they flow into the Colorado River watershed. Now, this is a really big and fairly important watershed because it has on it the biggest, at least I think it's the biggest dam in the U.S., the Hoover Dam. And that backs up Lake Mead, which is, I think, the largest man-made lake in the U.S. It's a reservoir, okay? And then downstream from that, you have the Grand Canyon. The Colorado River is the river that goes through the Grand Canyon. That's another thing I've said before. Yellowstone National Park up here is well worth you seeing before you check out. You know, if you can ever get out there, go see Yellowstone. Another thing I want to see before I check out is the Grand Canyon. I've never seen it. I came close to it twice, but never had time to stop. When I was crossing the country on my orders to go to my first ship, I didn't want to be late, so I wanted to make sure I got there in time. I thought on the way home, I'll check it out. Well, on the way home, I ran into car trouble, and before I even got out of California, and then I was running late, so I didn't have time to stop on my way back. I haven't been near it since, so I want to go see the Grand Canyon too. It's on the Colorado River, so it covers this part. Now, in between these are what we call divides. This one right here goes right down the Rocky Mountains, and this is called the Main Continental Divide. Everything to the east of that flows into the Atlantic. Everything to the west of this continental divide flows into the Pacific. Now, like the Mississippi goes into the Gulf first, but then ultimately to the Atlantic. Everything that goes here goes into the Pacific. Now, it doesn't go directly from the Colorado River because the Colorado River actually dumps into, ultimately down here in Mexico, into the Bay of California, I think it's called, even though it's in Mexico, and makes its way to the Pacific that way. Okay, Colorado dumps directly into the Pacific. Mississippi dumps directly into the Gulf of Mexico, but ultimately goes to the Atlantic. And you'll notice there are other watersheds here too. They don't name them, but between Georgia and Alabama, of course, is the Chattahoochee River that actually, whoa, here's Cormisha coming in. Let me get her here. There she is. All right, Cormisha's here. Well, I tried to admit her, but it wouldn't take. Okay. So now I should have 11 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Actually, I've got 12. We must have lost somebody too. Okay. So anyway, these are divides, things that, say that again? Was someone talking to me or just had the microphone on? Okay. And who's that? Yeah, I got you. I got you when you came in. Thanks. Okay, what separates a watershed is called a divide. The big divides are called continental divides, and this is a portion of the continental divide coming this way, and it probably extends on down here. This goes down the Rocky Mountains here. Everything to the east of that winds up in the Atlantic. Everything to the west winds up in the Pacific. May go roundabout. In here has to be a Sacramento River watershed that drains most of Central California. Okay, there's other watersheds that are in here as well. They just shown the big one. Obviously, the Rio Grande is a watershed. It goes into the Gulf down here. I don't know which river this is. It may be the Red River. It may be Cane River. I don't know what river this is that dumps into the Mississippi. But there's a divide between these two. This isn't a huge one. Now you might say, why doesn't the Mississippi drain anything to the east? Well, this is another continental divide. This one is the Appalachian Mountain divide. It comes all up here and keeps going up the continent like this. Everything to the east of that goes directly into the Atlantic, or some of this, like I said, between Georgia and Alabama is the Chattahoochee River that ultimately goes into the Apalachicola River and dumps into the Gulf of Mexico here. That's not part of Mississippi because it has its own entrance. What is the river that goes down into Mobile? Is that the Alabama River? It doesn't go into the Mississippi. The Tennessee does, but the Alabama does not. It goes into the Gulf of Mexico. Or that may be the Coosa or the Cahaba. I don't know what the name is, but we go in here. North Alabama, it goes into the Mississippi. Like I said, the Tennessee River comes in somewhere here, and it ultimately goes into the Mississippi. Over in Georgia, the Savannah River is here at the border between Georgia and South Carolina. It has its own watershed. There's the Ocmulgee, Oconee, Ogeechee. There's lots of rivers in North Carolina and South Carolina. They all feed directly. The Hudson River goes in between New York and these states here. That goes into the Atlantic here. So all those major rivers have their own watersheds. Okay, but these are the big ones. Okay, and the big divides are the continental divides, but every watershed is separated by a divide. This is a divide here. It's just dividing the Mississippi from whatever, maybe everything else goes into the Rio Grande. I don't know. Over here, this separates lots of rivers start in the Appalachians and go east. These go west. Ohio being one of the biggest here. Okay, so that's what a watershed is. It's a region that's drained by one series of streams and rivers. Okay, you have little watersheds building into bigger watersheds, These are the three biggies: Mississippi, Colorado, and Columbia. Lots of other smaller ones, and lots of smaller ones that lead into these, but these are the ones. What separates any two watersheds is a divide. Okay, and the continental divide actually splits where the water goes. The main continental divide, anything to the west of it goes into the Pacific, to the east goes ultimately to the Atlantic. Okay, any question on surface water? I can't get it to advance. Gotta click on the slide now. So let's move to, and by the way, there's an example here. I'm not sure it's all that useful. If on an annual basis the precipitation in a watershed is 914 millimeters of water, the actual evapotranspiration, that's evaporation and transpiration, is 686 millimeters, and 70% of the surplus percent. Oh, here comes David again. He must have had to leave. That must have been the one we lost, and he's back, but I already had him here. Okay, welcome back, David. Okay. 70% of the surplus precipitation is runoff. What is the percentage contribution of each component of the watershed budget? That's just sort of a made-up problem. If you want to follow it up, it's well worth a read, but I'm not going to take class time to look at it. All right, and remember, any two adjacent watersheds. Let's say that Valley Creek is a watershed. Well, I don't know what the next creek or stream is over from that. That could be a watershed, but then they probably are going to run together and form a watershed in a river somewhere. So little watersheds go into bigger watersheds. Okay. So groundwater starts on page 611 or 24-6. right-hand column, just a little bit there. So what is groundwater? That's underground water. Water that is saturated into the open spaces between rock and soil particles. Now, if you were a soil scientist, you would call that the pore space. Because I didn't say this back when we were studying the soils. I probably should have. But let me give you another soil science term here. Okay, and that is, here's a trick question. Would you say that soil is a solid, a liquid, or a gas? Anybody? Is soil a solid, liquid, or gas? Nobody's out there, are you? The answer is yes. Yeah, all three. A good, healthy soil is going to be 50% solid and 50% pore spaces. Those open spaces between the particles of the soil, and they're including between rock particles and soil particles as well. Okay? Open spaces, they call it pore space. Okay? When the water goes into the earth, if there was no pore space, there's nowhere for it to go. It all run off. But since it does go into the earth, you know there are pore spaces. So when it does go into those pore spaces, it goes in and percolates downward from the surface. Now, here's the deal. The groundwater is 25 times larger than the supply of surface water. So all the lakes, all the rivers, all the streams, all the ponds, everything that you can see of water on the earth, that you can see in some body of water like that, 25 times that is underground. Okay, that's a lot of water underground. Often it's within 100 meters of the surface. Now, what do we mean by that? That would be about if you took a football field and stood it on end and stuck it down into the ground from the goal line to the other end zone, the back of the end zone, that would be about 100 meters. Okay, that sounds pretty far. Okay, that's about 110 yards. It's about 330 feet. So it's pretty far down. So most of the groundwater, or often the groundwater, is located in that first 100 meters of the surface. Now, for some reason, it won't advance. There we go. So, how does groundwater get there? Well, anywhere on the surface or below the surface, if you have especially sand particles, they have large pore spaces, open pore spaces. They're very permeable to water flow. Gravel even more, okay? Gravel, because they're big chunks of rock, there are big holes, big gaps, big pores between those pieces of gravel. Very easy for water to flow through sand or gravel. We say it's very permeable. Now, I disagree with something they're saying here. Clay, they say, is low porosity. It can be. That's not an incorrect statement, but most of the time clays are not that low in porosity. What they're low in is pore size, okay? They have lots of pores, but they're tiny. Tiny, 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 tiny. Okay, I may have given this illustration before, but I'll give it again. Have you ever been to, say, a fast food place in the morning? You need a little pick-me-up, and you get a cup of coffee, and some of these fast food places are known for their very, very hot coffee, okay? Some have actually been sued because it's so hot, okay? But they'll give you these little swizzle sticks that you can suck just a little bit of coffee through, and that sort of cools it a little bit and keeps you from getting too much on your tongue and burning your whole mouth out, okay? So picture that. That's a very small pore size, okay? What if you were trying to drink your milkshake through that swizzle stick? You're going to blow your eardrums out trying to suck that milkshake. You're not going to do it. Well, that's what clays are. Clays, it's actually incorrect to say clays are low porosity. Sometimes their porosity is as much as it is in a sand. It's just that sand pores are large pores and a clay pore is incredibly tiny. It's like one of those little, way smaller than a swizzle stick. Okay, it is tiny. So the problem is how the water can get through. Even though the clay has a lot of pores, they're so tiny the water has to do like this. It goes laterally before it can find the way down, and then it goes laterally some more, and they're such small areas they go through very slowly. So it's impermeable either when it's saturated and now or when it's compressed. This is when their statement's true. If you've ever run over a clay road when it's wet, okay, you know it's slippery, okay. The reason it is all the clays, when they were building that road, they packed them down, they wetted it and packed it down. So in that case, yes, they've squeezed out all the pores. So there's low porosity then. So a dirt road, a clay road that you drive on, it can be hard as a rock because there are no pores in it anymore. Very, very few. So those can be very low porosity. But whether it's large porosity or small porosity, the pore size is so small, it's hard for the water to permeate through. So it still winds up being almost impermeable, especially when it's saturated. In other words, all the water's in there and it can't get out, then it runs off, or when it's compressed and then it doesn't have anywhere to go and it runs off. Okay, so this is sort of illustrating this. In sand or gravel particles, there's large pore spaces, large pore sizes, so lots of way for water to run down. And gravity is going to pull it downhill. In a clay, now if you were to add up all these pore spaces, they may have some of these a bit too close together, but if you were to add them up, you're probably going to come up with almost the same pore space that you have here. It's just the pore size is so incredibly small. And what they don't show is on the surface, when the clays get pressed, they really did shape them right, making them sort of flat plates. And when you press on those, they squeeze out the pore size and they pack together. Even though there may be great pores underneath, it's hard for the water to get to it because it can't get through. So for this bit of water here to go through, it's got to go around here, around there, around there, around there, around here, around there. Whereas here, they go straight down. Gravity pulls it straight down. Anything in here has to go what they call a tortuous route. It's like traveling on a crooked road rather than going on the interstate. It takes you a lot longer to get there because you have to make so many bends and turns. Some of the roads in our neighborhood, I swear sometimes you're going due north on them, sometimes you're going due south, sometimes you're going east, sometimes you're going west, because the roads just do this. They run around parks, around hills, around mountains. It just, they go in every direction. Well, to get from point A to point B, you have to travel a lot further than if you would if you went on the interstate. That's what they do in clays. They have small pore sizes. That's what makes it impermeable, and the route that the water has to take is so tortuous, so crooked, it takes a long time for the water to get through. Basically can be almost impermeable when it's either saturated, all the pores are filled, or when it's compressed and then it doesn't have any pores left. So that's the big differences in groundwater flow. Now, ideally for a soil, remember I said, is it solid, liquid, or gas? And I said the answer is all three. The soil particles are solid. The pore spaces are either gases like here or liquid like here. An ideal perfect soil would be 50% of the soil would be solids and 50% would be pores. And then 50% of the pores would be filled with liquid and the other 50% with gas, air. Why? Because roots need to breathe as well as they need water. So you have to have both the gases and liquid for that to be a healthy soil. This is not, okay? This would not be a healthy soil because every pore space is filled, there's no room for air. This is not because these are filled with air and not with water, okay? Water has a hard time getting through. So the optimum soil is one of those loams which has big pores, small pores. So you have some pores with air in them, some pores without. But you have about 50% of the pore space is water, 50% air, so the roots can breathe and they can also get the water and nutrients they need. So that's how groundwater flows through soil, whether it's sand, gravel, clay, silt, whatever. Now, groundwater tends to collect in what they call deposits. These are zones of saturation, okay? The precipitation falls. It falls on the surface. The water makes its way down. At some point, somewhere down there, it's going to reach an impermeable layer. That could be clays. It could be brown rock. It could be rock that's not going to let any water through. And then the water sort of piles up above that impermeable layer, collected on those zone of saturation. What we call the top of that boundary, of that zone of saturation, we call it the water table. And what they're doing, I don't know if any of you, probably most of you live in town and don't have this experience, but our place over in Georgia is out in the country. I mean, way out in the country. And it's about 8 miles from the closest flashing yellow light, about 10 miles from the closest red, green, and yellow stoplight. I mean, we're that far out in the boonies, okay? So we have wells there. They don't pump water that far out in this country. So when we were drilling the well at the house where we built over there, now we were sort of up on a hill, and they hit, I think the first place they hit groundwater, the water table, was around 125 to 150 feet. And they thought, oh, this is good. But it wasn't sustainable because they had to let it run, pump it for a full day, 24 hours. If it kept pumping, then they sunk the well right there. If it dried up, then that meant, nope, you're too far up. They had to keep drilling and keep drilling. They wound up being more than 300 feet, I believe it was. So it was more than 100 meters. One of the reasons for that is the people around us, not real close, but around us, have been irrigating like crazy, and they're drawing down the water table. So now everybody else has to drill deeper to get to groundwater deposits. Okay? Well, the top layer, wherever that is, at whatever time of year it is, these last couple years, the groundwater has been going up, the water table going up, because we've had good rainfall. There were many years before then it was terrible, and that's when we drilled the well. It was right before the first good water year started coming back again. We had had almost a decade of below average rainfall, so no wonder we had to drill so deep. Okay, now, but the water underneath that water table within the zone of saturation can move laterally because it can't move down anymore. There's some impermeable layer there, so it can move laterally. And what we call that are basically almost like underground rivers, and that's what an aquifer is. It's a subsurface layer of fairly highly permeable material, largely gravel, but some sand, very little clay and silt probably. And it says capable of producing water. No, capable of transmitting water, allowing water to pass through it. So yeah, they say producing. And usually in those aquifers, if they're really deep, they're called artesian aquifers. Now, an artesian aquifer Somewhere backstream from that, there is a lot of pressure on it. So that pressure makes the water, it confines water under pressure from a higher elevation. So now you go down to a lower elevation, and suddenly sometimes you'll have what they call flowing wells or artesian wells. It just happened to be the northern border of our county is called McBean Creek, okay? And my older brother's land is almost, it's in sight. If you go out of his driveway and look down the hill, you can, I think, see McBean Creek down there. I mean, he's that close to the county line, okay? And right on the other side, in Richmond County, on the other side of that, there used to be, I assume it's still there, an artesian well, a flowing well. Because everything from there, it goes uphill. So somewhere back there in Richmond County, there was artesian aquifer, but all the pressure from that land on top of that makes it come up there at the base now and feeds into McBean Creek. Now the reason I tell that is artesian water is coming from so far down into the Earth's surface. Now you're still easily in the crust. Don't think you're down at lower, you're not in the mantle, you're nowhere close to the mantle. You're not even close to the moho, you're not anywhere close. But you're far enough down that the water that's artesian water stays almost uniform temperature year round. And that's usually right around 70 to 72 degrees, okay? Which is great temperature, a wonderful temperature. That's usually what we try to keep room temperature is. I imagine here in this room we're between 72 and 76 degrees. That's a good, comfortable room temperature. Well, the artesian water is that way too. The farm just to the east of us back then was a guy who his family ran a meat packing plant. It's called Scott's Meats, and his name was Mr. Scott. And he had cattle. But about the time he decided to get out of the cattle business, it was Vietnam era. And in Vietnam, they had discovered they didn't always have optimum landing strips to land their planes and the supplies and things like this. They had to do with really rugged conditions. So they wanted to train their pilots, and there was an army base in Augusta fairly close to us, and they went down and found out Mr. Scott had some open land there that he had sold his cattle, he wasn't going to produce any more cows. They wanted to rent his property. He said sure, and they put an airstrip on his property. So they had a gang of soldiers out there living really roughly, in tents and things like this, no great base housing, and they were learning how to develop airstrips and out of nothing, out of really rugged hilly land, how to land aircraft, how to guide aircraft in. That's what they were doing. Well, that first night when they did night operations after they started that thing, I hardly got any sleep because about every 15-20 minutes there was a plane taking off right over our house. It was pretty bad. But they had to carry out tanks of water because they didn't have a good water source in that field. And that was okay for drinking and cooking and stuff, but it was pretty miserable when it came to shower time. But they found out just a few miles, like a mile or two up the road there, was that artesian well. And when they found that, they went up there and made a contract with that guy who owned that land. It was somebody else. And that's where they put the showers. And the reason is, in the summertime, the heat like we have now, that water coming out of there was around 72 degrees. That felt nice and cool, okay? In fact, probably cold this time of year. But in the wintertime, when it was like 40 degrees, it was still 72 degree water because it was artesian water. It was from an artesian aquifer, confined under deep water, under pressure, from a higher elevation. It makes its way down. So this is sort of what we're talking about. Down here somewhere you have either bedrock or you have really dense clay layer, somewhere in there. Okay, above that you have permeable soil. It may be somewhat permeable, a little permeable, whatever. And above that you have permeable soil. Okay, the difference is this lets water go through it, but because of the impermeable layer here, the water piles up on top of that, and then this is what we call the water table. So if you're drilling a well up here, even though you might get a little bit of water in here, you have to get into the saturated water table before you can have a good reliable well. Okay, now somewhere downstream from that, if the surface and the water table collide here, the water table's up here but the soil surface dips below it, you may form a naturally forming lake here. But then you have more soil here on top. The water table makes its way down here, and then this produces a spring. That could be artesian. It doesn't sound like it is in this case. Okay? On further down, and this could be a river going through here, or it could be a little pond or lake here. Somewhere further down, before you get to the coast, you have another place where the water table breaches the surface, and then you have what they call a swamp here, okay, or a lowland. You can sometimes call it that. And there may be more soil on top here. Ultimately, some of this saturated water goes right into the ocean without ever coming to the surface. Other places, maybe if this is a river, it makes its way down and dumps into the ocean, okay, or on the other hand. But some of it could come into the ocean through a lower layer. Okay, so that's any zone of saturation. Here's your zone of saturation here, the bluish, like grayish area. Your permeable water above that's not, or soil above that's not saturated, is what it goes through to get there. The impermeable layer down here, which is usually bedrock. For us in this region, it's usually limestone, okay, but it doesn't have to be. It could be granite, whatever, and it could be a really dense clay layer too, but that's keeping the water from soaking in, so it moves laterally from here on. Okay, excuse me. I taught my last class. All this weekend I was out in very hot conditions, doing a lot of work outside, most of which was very dusty, very full of pollen and all sorts of junk from plants and soil. So my throat's raw, my nose is stopped up, everything's dried out because we drove back this morning and we didn't drink lots of fluid on the trip, so we wouldn't have to be stopping, not with COVID going all around, and we were in a hurry to get back too. So I'm water deficit today, so that's why I've got to stop every now and then just to to rehydrate, basically. Okay, now this slide shows your artesian aquifer. Now this is a bit simplistic here, okay. If somewhere down here you have an impermeable layer, and maybe one even above it, but in between you have a very permeable layer. Now this is a bit unrealistic to show this exposed to the soil, like to the air like this. That doesn't usually happen. It just wouldn't. You have more soil and stuff on top, and the water makes its way through the permeable layer here. Maybe this just continues here without the impermeable layer. It makes its way in here, but makes its way really, really, really deep. And when you're drilling a well here, you have to drill sometimes through a lot of overburden, a lot of land. But when you do reach into the aquifer, all of a sudden the water level comes up to here. Now this is what doesn't make sense here. This is where if that's the water level, then this should be soil on top of it. You wouldn't have water on top of that. That's the water level right there. Okay, so this should be soil up here, and they just didn't draw this well. Okay, but that would then be an artesian well, and that I think is what we've got on the farm, because we had to go really deep to get into it, and once we did, it's nice. I mean, very sweet, clean water. Okay, now on downhill from there, you may actually be below that pressure level of the water table here, but it's down, the water is way down here because of this impermeable layer doesn't allow it to go up. Well, then if there's either someone drilled a well there or there's a natural opening there, that's where the water comes bubbling up. That's where that artesian well was that the soldiers used. Okay, there was also a swimming area called McKinney's Pond. No, not McKinney's. I'm sorry, I can't remember the name of it. It doesn't matter. Down in Millen, Georgia, south of us for a ways, that was fed by an artesian spring, a flowing artesian well. And boy, that pool in the summertime felt so cold because it was constantly being replenished by this nice 70, 72 degree artesian water. I mean, really, really cold. Okay. And that made its way to the surface. They channeled it down into the swimming pool. It was cold. You would turn blue almost in it. Okay. So that's why you have what they call artesian wells or flowing wells, or an artesian well that comes really close to the surface once you drill through that impermeable layer. Okay, that's groundwater deposits. Now, where we go next is freshwater as a resource. This is over on page 613 in the big book, or 24-8 in the smaller books. Okay. And this should come as no surprise to you. Freshwater is a resource. It's required for life processes, for industrial society, for everything that we use. We just can't use salt water for just about any purpose at all, except to sail over. Okay, that's about all it's worth. Now, this is an incredibly large number. The average U.S. usage, and by the way, we're the biggest energy hogs too, but water hogs on the surface of the planet. We use way more than just about any other people group on the planet. I'm going to pull out my calculator just to give you an idea of what they're talking about. And it sounds just completely unbelievable until we'll break it down a little bit later. Okay? Let me get the calculator up. A liter is about the size of a quart. It's a little bit bigger than a quart. So the average U.S. usage is about 570 liters per person per day. 570, if you divide that by 4, that would be 142, let's just call it 145 because a liter is a little bit bigger than a quart. Let's call it 145 gallons of water a day. I don't drink that much, I promise you. No, we're not talking about drinking. About 40% of that is agriculture. Hey, we're concerned. If someone's having to produce the food, they're having to use water to do it, so therefore we are the ultimate consumer. If we're consuming that food, we're doing that. So that food could be vegetables, like raised in a greenhouse or out in a pasture or field. It could be meat that you've been fed and watered, okay? Lots of water. And the food they eat, you grow, and that requires water. About 40% of that 145 gallons or so that we use is for production of electricity, because we're the biggest hog of electricity on the planet. Okay, and about 10% is used industrially, because we're using products all the time, and many of those products, most of those products, use water either as part of the process or part of the material. Okay, you have it in water. Okay, so that's industrial. So you add that together, and 10% of that then would probably be our personal use, which we would drink, wash our clothes, flush our toilets, and that kind of thing. That would be about 10% of that would be out of about 140, no, I'm sorry, 14 to 15 gallons we would use between drinking and cooking and flushing and washing dishes and washing clothes and that kind of stuff. That would be probably close to 14 to 15 gallons a day per person. Okay, it's a lot of water. Most of our supply comes from surface water. Even though groundwater is the biggest, there's 25% more, no, 25 times more groundwater than their surface water. Its surface water is just there. It's there. It's available on the surface. Now, there's some downsides to it for sure. There's more sediments, more bacteria, more pollutants, and all the surface water depends on rainfall, precipitation. Now, if y'all were in the area, the Birmingham metropolitan area, I'm trying to think, I would say between 5 and 10 years ago, there were, it seems like 2 or 3 summers where Lake Purdy, who is the major surface water contributor to the Birmingham Waterworks Board, I think it's Lake Purdy, was down, I'd say 15, 10, maybe even 5% of its capacity. And that was getting dangerously low, and they had to go, I can remember at least one year, and it seemed like 2 or 3, that they went to some type of water rationing. Now, we didn't get super bad, but we did get things like, if you had an even numbered house, you could only water your yard on even numbered days. On odd number houses, could only do it on odd number days. Okay, so they did put some things like that. And then there was a time they said no watering of yards whatsoever. Okay, and then they had times, of course they had times when there was no burning whatsoever, because there was just not the water supply available. So, disadvantage of surface water: more sediments in it, more bacteria in it, more pollutants in it. So that means you got to treat it. They treat it with chemicals to kill the bacteria. They treat it by purifying it to separate from the sediments and somehow get all the pollutants out of it. Okay? The precipitation that falls is clean, but as soon as it hits the earth and gets mixed up in the rivers and streams and lakes, it's polluted. Okay. Now, they say more than 40% of our fresh water as a resource comes from groundwater. So when they're saying most of the supply comes from surface water, that means close to 60%. Okay? But it's not a huge majority. Now, like I said, at the farm, all weekend I was drinking, flushing, bathing in, fresh groundwater, not surface water, because we had the well. It was groundwater. And the wonderful thing about that is relatively free of bacteria, relatively free of suspended particles. Okay? It's pumped to the surface, and that takes energy to do it. So it's not free. Okay? It takes energy. We pay for the electricity to pump it to the surface. But once it's there, it is good water. Okay? No chemicals have been added. No treatments have been made to it. It's just good, pure water. My older brother lived close to a mile down the road from us. a little bit closer to the creek down there. And his water, he didn't have to drill as far to get it, but it always has a little bit of suspended particles in it, even up to being sand particles. So he has to have a filter outside of his house to try to separate all that. So it's still relatively free of bacteria, so he doesn't have to treat it, doesn't have to add chlorines or something to it, but he does have to clean it. My younger brother, his well is pretty good. I think ours is a little bit better. My sister, on up the road a little bit further, anytime it rains, hers water supply, her well, gets suspended particles from clay in it. It turns red. So she has to go and get water from another source until it settles out, because there's too many suspended particles. So even groundwater can sometimes get messed up. Okay. And the cost of pumping it to the surface, where surface water is already there. But then you have the cost of treating it. So I think the treating it costs more than pumping it, because generally you're going to have to pump the surface water anyway to get it up a water tank. All right, that's it for fresh water. Let's move on to salt water. Now, before we leave, when we go back to that thing of how much we use, home freshwater use. Toilet flushing, almost a fourth of it, 24.2%. Clothes washing, a little over a fifth of it, that's 21.7%. Showering and bathing, washing up, that kind of stuff, would be a little bit more than a sixth of it. Your faucet use, that would be drinking, cooking, everything else you just get out of the faucet, it's a bit less than a sixth of it. And then the sad news is leaks and other things, almost a fifth of the water is lost, is wasted to other purposes. It leaks. Unfortunately, where we live in Birmingham, it seems like you can see some leak, some water leak coming out of a road. You know, seems like every few weeks you see another one, because our infrastructure is so old. The pipes and things that carry the water, they get pressure on them, they resurface a road, they crack the things, break them, they get a little contamination in them. People can't drink that. It gets muddy colored or something like that. They have to come in, dig that up, and put in new piping or new whatever that failed earlier. They have to replace that. And so that's where that leakage stuff comes from. Now, out in the farm, hopefully we don't have any leaks, or many, but surely there probably are some. Okay, so that table is on page 613 or 24-8. Now, for any of you who are interested, I find the closer look on pages 614 and 615, that's 24.9 and 24.10, to be a really good treatment, literally, of water quality and wastewater treatment. Now, you may find this a grotesque thing for me to say, or just gross thing for me to say, but it's so true. Every drop of water you drink or use in cooking or bathe in at one time was wastewater from something or someone else. Okay? What we do, this sounds gross, but it's true. Our wastewater is collected at wastewater sites somewhere. I'm talking about here in the city, and they treat it, they remove as much bacteria, they treat it chemically, they remove sediments, they remove as much as they can, and what they pump on downstream is fresh water. Go on down the river, go on down to whatever. The next city down is going to be using that. That was our wastewater. They're using it as fresh water. Okay? That's what happens, folks. But even if it wasn't treated by humans, it evaporates off that waste, goes back into the sky, and comes back down again, and someone uses it. Hey, I wish I knew the exact percentage, but it could easily be that at least one molecule of water in your body right now could have been in a former president's body at some time, or a former criminal's body at one time. I mean, who? Okay, the thing is that if you think about it, water is water, and what we've got is what we've got, and we've been basically using that same water over and over, yeah, basically almost forever. Now, it's not quite totally true, but it's largely true, because if you think about what photosynthesis does, is take energy from the sun, water from the ground, and carbon dioxide from the air, and turn that water into a carbohydrate, a sugar. And then the plant may make more complicated carbohydrates like starches, cellulose, wood, things like that. Okay? So that water got sidetracked and became a carbohydrate. Maybe a fruit, a nut, or something like that as well. Ultimately, we're going to use it, and we take that carbohydrate, and what our digestive process does is break that down into carbon dioxide and water. So that water that went into the plant may not be the same drop of water, but the H's and the O's may have come from different sources, but they all wound up back as water. Or not all of them, but a lot of them wound up back as water again. So it's just amazing if you were to try to track it. Most of the water that we bring into our body leaves our body probably within a few hours. Okay, most of it. Some of it is actually used, but at some point it's going to also cycle through. And it goes on downstream and cycles through somebody else's body, and or animal's body, or whatever. Okay, so this blurb talks about water quality and wastewater treatment, and it is a fairly instructive blurb. I would say it's well worth a read. Okay, that's in the sort of lavender or purple box that takes up most of those 2 pages, 614 and 615, or 24:9 and 24:10. Okay, they also show on the next page of figure 616 a water treatment plant, and to me that would not be a good place to work, but people work there. The smell, I would think, would be pretty rugged sometimes, but people have to be there and take care of it. The next figure other than that shows groundwater being pumped from the ground, used for irrigation. They also use a lot of surface water for irrigation. So it's pretty incredible how much water we do use, because that irrigation water, we're beneficiaries of the production of that water. All right, now we're ready to go to 24-2, and that's seawater. Second section. We've been in quite a bit long in the first section. Seawater. 70% of the Earth's surface covered with seawater. And when I say covered, I mean covered. Average depth of 3,800 meters. Okay? Now, this is going to be an approximation. 3,800 meters. A meter is a little bit more than a yard. So if you divide that by I'm going to say, this will be a rough estimate, 1,700 yards per mile. The average depth of seawater of our oceans and stuff is about 2¼ mile deep. Okay, now that's on average. It's just on average. There are many places it's way deeper than that, and of course in many places where it's shallower than that. But on average, about 2¼ miles. Okay, that's pretty incredible. Now, only 30% of Earth is dry land. The average altitude of that dry land, now this is average, about 830 meters. So think about that. The land that's underneath the oceans is way deeper than the land that's above sea level. Okay? So, pretty amazing there. And I think I've said this before, we understand less about the ocean than we do about outer space, because we just don't know it. Most of the ocean is still unexplored. We have clues of what might be down there, but we haven't been there to see. So it's pretty amazing. Okay? Now, let's talk about the various components of this. These are all saltwater, seawater reservoirs. The biggest, of course, are the oceans. An ocean is a continuous body of salt water that basically covers most of the Earth's surface. Okay? 3 principal reasons. Okay? The Atlantic Ocean is the middle child. Okay? It's the second in size. Pacific is way bigger and way deeper. Okay? Pacific Ocean, bigger and deeper. The Indian Ocean is an ocean, but it's the smallest surface area. Still a pretty big ocean. Okay, that's what an ocean is. Continuous body of salt water covering huge regions of the Earth's surface. Now, what's the sea, on the other hand? A smaller region distinguished by special characteristics, and they don't really specify those. Now, in your text, you might be able to find a few more details there, but they just say special characteristics. And what that means is they kind of have a boundary, not a rigid fixed boundary, but kind of a boundary. Here are some of the major seas. Okay, first let's look. Now, they've drawn the map so that the center of the map is right here through Greenwich, England. Okay, there's your prime meridian right there. And you go east and west from there. Well, the Atlantic Ocean is this big, long ocean here. Goes from way north to way south. Snakes its way between Europe and North America, between South America and Africa, and everything in between. Okay? That's the Atlantic Ocean. Indian Ocean over here, mostly in the southern hemisphere, though it has some of it is above the equator here. But the Pacific, huge portion of it over here in the eastern longitude, and huge portions over here in the western longitudes. Okay? Huge sea, ocean. Okay. So the seas, smaller regions of salt water still, distinguished by special characteristics. They mention several here. Here's the Mediterranean Sea. It's almost completely enclosed. It's not exactly. It wouldn't be salt if it was. But you know, here is the Straits of Gibraltar between Spain and Africa. Pretty narrow there, but you know it is. If you wouldn't want to swim it. I'll put it that way. It's not that narrow. Okay, it's not almost touching like it looks like here. Upstream from that, there's also the Black Sea, and upstream from that is the Caspian Sea. Now, I would be surprised this is very salty, but it may be. It may be that's a big enough body of water there. You have the Arctic Sea up here, north of all the Atlantic and Pacific. Okay, Arctic Sea there. Here's the Bering Sea here. Now, it's the thing that separates the Bering Sea, Siberia over here, which you just barely see here, Alaska here, and then the um, Aleutian Islands that go down here. That sort of defines the Bering Sea. They mention the Gulf of Mexico here. They don't show it on the map, but there it is. That's the Gulf of Mexico. Now, what separates a gulf from a sea is not real clear. Sea is usually a bit more contained. The Gulf has a bit more opening. But so you see there's a big opening here and a big one down here. But see, not only that, the Caribbean Sea. That's the sea that's sort of defined by these islands here and Central America and South America. This is basically what they could mean by the Caribbean Sea. That's Cuba. I think that's Hispaniola is the name of it. That's where Dominican Republic and Haiti are. There's Puerto Rico there. I think that's Jamaica there. I'm not sure, but I believe it is. Okay. Those sort of not exactly bound the Caribbean, but that's why the Caribbean Sea. Sea of Japan is between the proper continent of Asia and the island chain of Japan. Again, it's not a fixed boundary because there's plenty of places for it to leak out. If you were around in Vietnam time, this was called the South China Sea here. Okay, that's where a lot of the activity was. Okay, these are the Philippine Islands here. These are islands of mostly Indonesia, though there's a few countries there that aren't part of Indonesia. Here's Australia, of course, down here, and New Zealand over here. Near South America, there's a Weddell Sea down here. That's one place where the South America either juts out or juts in, whichever you want to call it. Ross Sea is over here, where it's hard for them to draw Antarctica accurately because you've spread it out, because it's a really tiny area, a fairly tiny area, so it makes it look like these are flatter surfaces. They are. These are definitely seas here. Okay, those are just a few of the seas. There are many others that were not named here. They mention gulfs. There's also, this is a bay here. Hudson Bay is not mentioned. This is the Persian Gulf is right here. Okay, the Red Sea is right here. They didn't mention that one either. Actually, within the Mediterranean, the one that comes up between Italy and what used to be Yugoslavia and some of that area there, this is called the Adriatic Sea here. Okay, it's bound by Italy. You know, it's basically part of the Mediterranean, and then the Aegean Sea is the one right around the Greek islands. It's hard to see them on here. Okay, so you do have other seas out there. So they can call them gulfs, they can call them bays, they can call them a variety of things, or sea. Okay, so let's look at, those are the big boundaries, the macroscopic picture. Let's look at what seawater is all about. Okay, what makes it? We call it seawater. Oftentimes we call it salt water. Okay, because it has high levels of salinity, which means masses of salt dissolved in the water. Now, this is supposed to be a definition here, but they did a really lousy job of stating it. What it's supposed to read is the mass of salts in grams dissolved in a kilogram of seawater. Okay, now if you know your metric prefixes, kilo means 1,000. Okay, so the mass of salts in grams dissolved in a kilogram of seawater. So that is 1 part per 1,000, basically. That's what your salinity is measured in. It does not change. Now this is sort of a gross statement here. Does not change with changes in water temperature. I think what they really mean to say, it does not change much with changes in water temperature. Of course, if a water temperature is hotter, you can dissolve more material. You know that. Hot tea dissolves sugar better than cold tea does. You know there is a relationship there. But you see, the seawater usually doesn't change temperature that much, and the amount of salt contained in it usually doesn't vary that much with temperature. Now this is where they've made an error. It says it averages 35% with a 32 to 36% range. That's totally wrong. This is a symbol, and it's correct in your book. It's not percent, and I can try to write it correctly there. In your book, if you'll notice it, now this writes with a red. I maybe could do blue, but this is supposed to be, yuck. There's supposed to be an extra, is it? You shouldn't be interrupting me. No, I'm just kidding. It should be written like this. It's not percent. And I didn't put the red line there. It did its own. It's per thousand. Percent means per hundred. 100 centimeter is 100. Yeah, that percent means out of 100. Okay, this should be a 0/00. That's per thousand. It should be 35 grams per thousand grams. Okay, with a range of 32. So that really would be 3.5% with a range between 3.2 and 3.6%. But the actual way they say it is per thousand, and in your book it's correct. On this slide it's wrong. That should be the percent sign with 2 little zeros under it, not 1. Percent sign means per hundred. This means per thousand. The concentration is increased by evaporation, because once water evaporates, that concentrates the salt. Also, when water freezes to form ice, the water freezes but not the salt, so the salt's left behind. So it increases by that, but it's decreased by heavy precipitation, because think, rain and snow is pure water. So when that falls on the ocean, that decreases the precipitation, the percent of salinity. Okay, but also ice melting, because ice is fresh water. When it melts, then it dilutes. River inflow, because rivers are largely fresh water. When they flow into the Gulf or the ocean or something, they then decrease the salinity. Okay, the proportion of ions is relatively constant, and we'll see that on the next slide. But it also, seawater and all water contains dissolved gases, mostly nitrogen and oxygen near the surface, because that's what's near the surface. But it also has large amounts of carbon dioxide. Why? Because plants and animals breathe out carbon dioxide. Believe it or not, plants do breathe out carbon dioxide. Green plants take in carbon dioxide, but other plants, and even the roots of green plants, breathe out carbon dioxide. So there are large amounts of carbon dioxide in not just seawater, also in freshwater as well. And just a quick look at this table. These are the highest salts, ions, that you have. A salt is an ionic structure. Sodium chloride is the most common. That is actually what we call salt. Sodium and chlorine. Okay, now they don't always go together, but they largely do. Sodium's a positive ion, chlorine's a negative ion. That means chlorine's picked up an extra electron, sodium lost an electron. Sulfate's a -2 charge, that means it's picked up 2 electrons extra. Magnesium's a +2, it's lost 2, okay, electrons. Calcium is just like sodium, it's lost 2. They're right below each other on the periodic table. This is incorrect here. It's correct in your book, wrong here. This should be K is a single plus. If I can get the pen to write. That's a plus, not a minus. Bicarbonate is a minus, but that minus shouldn't be down here. It should be up here. Okay, you don't put the minus down with the 3. Bromine is a minus, okay, just like chlorine is. Okay, The rest of this is pretty close to accurate. So the largest concentrations of ions, in other words, the salts that's in there, it's sodium chloride. And that's why we call it salt water, because that's table salt. But you have plenty of other things like sodium sulfate, magnesium chloride, calcium sulfate, calcium carbonate. I mean, you have lots of other things in there. You have calcium chloride, calcium sulfate. I mean, all these can mix up in any ways they want to. Okay. But the predominant ones are sodium and chlorine. Potassium is in there too. When they say, I don't know if you notice on food packaging these days, they brag about sea salt rather than table salt. Sea salt has both sodium chloride and potassium chloride in it. That's what makes sea salt. Okay, just there's a lot less potassium than there is sodium. Okay. All right, I guess we're going to have to end there or Valerie's going to get all over me. Oh, wait. This picture too. If you had 1,000 grams of seawater, you would get 35 grams of salt. That's where this comes out. That's not percent, that's per 1,000. 35 grams of salt, leaving you 965 grams of pure water. Because 35 grams of that were the salts that were in the seawater. Okay. We will stop there and pick up with movement of seawater next time. There are a couple of examples there that you could play around with. They are pretty easy to do if you want to, but we'll pick up on page, oh, there's my pencil, on page 620 or 24-15 next time. The top of that page is estuary pollution. Remind me, we need to talk about that next time. Not a big subject, but it is a subject. All right. Now, that's it for today. So we've still got the movement of seawater. We got the ocean floor, and that's it. We will easily finish the chapter next time and have plenty of time to do the lab, and we can do it together as a group, or y'all be able to do it individually if you'd like. So let's move now to the lab. Okay, now let me go on and end this. Okay, and end. No, yeah, but I'll show you what we're going to be doing in lab. Okay, now where you're going to go is Blackboard. Okay, let's see if I have Blackboard open now. No, I don't. Okay, I thought I did, but I didn't. Okay, let's go to Blackboard. Oh, you can't see this. Let me get screen share so you can see what I'm doing. Come on, where's screen share? Okay. All right. Can y'all see this? It says Google. I'm using Google Chrome, so that's why you're seeing Google. I'm going to try to move this taskbar out of the way so I can see things well too. Okay. So in Google, you won't go to Employee Portal, but that's where I go to get the Blackboard. However you get the Blackboard, go to Blackboard. All right. You sign in however you sign in. I'll sign in however I sign in. Okay. This is a pain in the neck sign in my mind too, but it's there. That's what we have. Okay. Once you get in Blackboard, go to Courses. I don't know why they go to Activity Stream. It's as far as I know, useless, completely useless. Okay, then scroll down till you find this course. I have a lot of courses, so let's find this one. There we are. Okay. Now I sure hope, yeah, I know I've got it here. Okay, under course content, there's today's lecture. Okay, under course content, scroll down until you get to laboratory simulations. We've been here before, remember? All you have to do is click on that and it takes you to the web link. Okay? Once you get to that web link, you go to simulations. When you go to that tab, go down to your earth science. That's what we're dealing with, earth science. Click on that one. It takes a while. Now, at this point, and of course Valerie's in the way again, I got to move her out of the way. Okay. All right. We're going to scroll down here until we find the greenhouse effect. And unfortunately, it's not listed under G for greenhouse effect. It's listed under D for the greenhouse effect. Okay. So you scroll down, scroll down, scroll down until you get here to the greenhouse effect. Okay. Click on that one. Okay. Once you get that up, go to this circle here with the triangle inside. That means you're going to start it. Okay, so I'm going to start it here. So click on that. These are all instructions out there. Now this one takes a time to load. Now this is a Java simulation and some of you may not be able to do it. So watch the video. You can go back and watch the video on this one. It takes a while for it to open, and if you can't get it open, watch the video because we're going to go everything today that you have to do. And again, I said this takes a while to open if yours will open it. In my second half of the spring term, okay, as soon as it starts here, stop it. Go down here and pause it, okay, because it was trying to start without you. Okay. Now Valerie's in the way. No, Roy's in the way now. So let me move Roy over here. Okay. Now, what we want to do is at this point, record your initial conditions. So if y'all are going to start writing, here's what you write first. Okay. The first is the atmosphere during. And here's multiple choice here. Today, 1750, or the Ice Age. Ice Age was way before 1750. 1750 was shortly before the American Revolution. So this is today is now. 1750 was back at when we were just being colonized in this country, and the Ice Age is way before that. So we're going to start with today. Okay, so that's the first one, today. All right. Now, record these other initial conditions for today. The first is greenhouse gas composition. Wait. I'm sorry. Greenhouse gas concentration. That's what we do next. Where are we today? We're in the green bar. Okay, you see the green bar is more on the lot side. The blue bar is more on the left side, even toward none. So we have lots of greenhouse gas concentration. So that's the first, and again, multiple choice, blue bar, purple bar, green bar. Today, we're in the green bar. Okay. And you also notice today is green. Okay. Now we move down to greenhouse gas composition. This is the next thing we list. Okay. 4 greenhouse gases. Water. Okay, that's measured in percent relative humidity. And what that means is how much water does the air contain compared to how much it could hold. Well, it's about on average 70% saturated. So 70% relative humidity. Write that down. Number 2, carbon dioxide. That's the big one they talk about today. 388 parts per million. Remember when we were talking about salinity of the ocean, that was parts per thousand. This is parts per million, ppm. The CH4 is methane, another really powerful greenhouse gas, 1.843 parts per million. So not nearly as much as carbon dioxide, but it's still a significant greenhouse gas. After that, it's nitrous. I think this is called nitrous oxide. It's N2O, and that's 317 parts per million. So not very much of that at all. Okay? So those are your 4 greenhouse gas composition. Initial temperature, you come over here and they say, and I would say go on and do it in degrees Fahrenheit. That's what we're used to. Okay, -9 degrees Fahrenheit, that's pretty cold. Okay? But that's assuming, okay, now here's what that was. This is if our atmosphere did not trap heat. Our atmosphere does, and it's designed to trap heat. We have to, otherwise we wouldn't live. Everything would be frozen. We would be an ice planet. We wouldn't be a water planet. Okay? So yeah, we wouldn't exist. So if we did not have some greenhouse gases, our atmosphere would be, our temperature, initial temperature would be about -9 Fahrenheit. Okay. So that we do, those are our initial conditions. We record those first. Now we come down here and start. Now, the last time I did this, it wasn't here. So I'm going to see how this runs. I'm going to start the simulation here. Now, what you're going to be watching for is what is your initial, what is initially happening to the temperature. So once I start here, go back and look at your temperature and see what's happening with it. Okay, to me it was surprising. The next question is, what are your initial photons? Now the photons up here are either sunlight photons, meaning this is visible light coming from the sun. This is where the energy from the sun is making its way through our atmosphere and reaching the earth. After a while, you'll see infrared photons. This is photons that have been, once they hit the surface of the earth or come into the earth's atmosphere, they drop in energy and become heat. That heat is what gets trapped. Okay? And the greenhouse gases are some of the major things that trap it. So, the things to watch for: what initially happens to the temperature, and what are your initial photons, what's initially happening to the photons. So I'm going to start the simulator and you watch for both things. What do you notice happening to the temperature? It's actually going down. Yes. Okay. And what photons do you see coming in? Sunlight photons. So those are the next 2 questions. Okay, after a time, which photons do you start seeing? Oops, I saw one, I saw another, and now you get to see more infrared. What's happening to your temperature now? It's going up. Once those sunlight photons, some of them change to infrared, and the infrared starts taking over, that's when your temperature goes up. We have to have some greenhouse effect over our atmosphere, or else we're too cold. Okay? Now, you sit here a while and watch it happen. What seems to be your equilibrium temperature? So watch that, and when it finally stops going up and sort of stabilizes, you don't have to be exact, but where does it seem to stop? Yeah, that's Kelvin. Let's do Fahrenheit. About 44 degrees Fahrenheit. Yeah, 45, 44, 45. And now it's going up a little more. Okay, so it may not. So we'll come back and look at that. Okay? Now, maybe up to 48 or 49. 50. Let's just end it at 50. Okay? I'm going to stop it. I'm going to stop it or pause it, and I'm going to reset everything. Okay? Now, yes, and reset all settings. Yes. Okay. Now, before we start it again, okay, let's go to 1750. Okay. Now notice here, what's our greenhouse gas concentration now? It's, you say pink or purple, whatever you call that. Okay. Yeah. Okay, that's the one, and that same color as this. So let's see the greenhouse composition now. Guess what? The water concentration is about the same, 70% relative humidity. Did y'all write that down? Okay. How about carbon dioxide? What was it before?
388.
And now it's down to 280. So that's dropped significantly. Okay. Okay. Making sure I'm not skipping anything. Okay, how about methane? What was it before?
1.843.
Okay, and this, okay, parts per million, this is less than half of that. Now, notice the difference. Remember before we had buildings, factories, lots of houses. Now we have occasional farms, and that's all. Okay, but you have to write that down. Okay, so your methane is dropped by less than half. Okay, how about N2O? What was it before?
0.317 parts.
It was 0.3, or you said?
Yes, sir. 0.317.
Okay, so now that's dropped by not, it's not dropped as much, but it has dropped a little bit. Okay, now those are our initial conditions again. Here we're going to start the simulator. Okay, now when we do, we're going to notice the same things again. Okay, when I start it, see what the temperature starts as. About the same as it did before, and it starts dropping. So notice those things before, about the same temperature, and it's dropping. And what kind of photon? Sunlight photons. But notice it's taking a little bit longer before you finally see the infrared photons. Do you see as many? Oh, and by the way, once you see those infrared, you see the temperature starts rising. So let's see what it goes up to. Okay. What seems to be the equilibrium temperature now? See, did we get up to 50 before?
Yes, sir.
Okay, we gonna make it this time? Doesn't look like it. Maybe 46, 47. We came pretty close, 48 maybe. If we went long enough, we'd probably make it, but if we went longer on the other one, you probably would have broken it. Okay, you can put down whatever makes sense to you. So let's stop it again and go to the Ice Age. Have you got your jackets on now? Yeah, put on your coats. There's the Ice Age. You don't see anybody around anymore, and you see snow build up here. What did our greenhouse gas concentration go to? Blue bar. Okay. And carbon dioxide, we don't know. It's not clear. So it's unknown on the water composition. It's, oh, yeah. I need to reset. Sorry. Let me reset. Reset all settings. Okay. Oops. I forgot to do that. Okay, Ice Age. We still don't know the water composition. What is our carbon dioxide? And what was it? And today? 380 something?
No, it was 388 today.
And,
388 today.
and what was it in 1750? 280 something, wasn't it? Anyone record that? Okay, well, we'll go and see. 280. Okay. So, yeah, okay. Be writing all these things down, or you can go to them if you can get to them and do them. So, yeah, carbon dioxide was 280 in 1750, 388 in today. Ice Age, 180. Okay. How about methane? 0.380. What was it before? Today was 1.84. 1750 was 0.73. Okay. Ice Age, about half of what it was, not a little over half of what it was in 1760, 50. Okay. And nitrous oxide, or N2O, 0.215 in Ice Age, 270, 0.270 in 1750, compared to 317. So all the greenhouse gases, much less. Okay, write these down. I hope you're getting them. If you need me to go back, I'll go back and do. Okay, now let's start the simulator. Okay, what's your initial temperature? About -1. It starts dropping. Your photons are coming down from light, sunlight photons, and temperature is still dropping. It's dropping longer and longer. I haven't seen an infrared yet. Oh, there's one and two. So you do start getting some. But guess what? It takes a long time for those infrared photons to start getting close to what your light photons. But after a while, they get there. What's your temperature gone up to now? Yeah, Fahrenheit. And it crept up to about 17, 18 now. Looks like it's going to bottom out. I mean, not bottom out, but equilibrate in the low 20s somewhere. That's why it's an ice age, because the average temperature on the surface of the earth was now down here below freezing, below where ice forms. All right. I did ask a couple more questions. I forgot to ask those here. Let's go back and let's see. Let's go back to today. What do we notice in the air? What do we notice in the air? Anyone know what that means? What it represents? Satellites, yeah. And they didn't show jet planes, rockets, to launch those satellites. I mean, all sorts of stuff we got up there. How about on the ground? I mentioned this one before. Big buildings, factories, businesses, houses galore. Okay? How about 1750? What you notice on farm only? Nothing much in the sky at all. No planes, no helicopters, nothing. Certainly no satellites. Ice Age, nothing on the ground, nothing in the air. What people were, they were probably underground if they could get there. They were just barely hanging on. If there were even people alive then. It may have just been animal life. Who knows? I don't think anyone had it back then. I forgot to ask those questions here. Okay.
Those questions are going to be on the test.
On the lab, yeah. What disappeared from the sky when you went to 1760, 1750? What disappeared from the ground? And then in the Ice Age, what disappeared from the ground? Because there wasn't anything in the air on either of those. So basically, all pretty much evidence of life disappeared on the ground. So, okay. Oh, thank you so much. Okay. 2 minutes early. What in the world is wrong with you? But it's not a bad time for me to pull it up because it'll probably take me 2 minutes to call it. Okay. So here we have Capri is still here. That's good. Caitlin's still here. Cormisha's still here. This sort of goes alphabetical order by your first name. David's still here. Don's still here. Okay, let me scoot down a little bit here. I tell you, I'm having trouble getting my fingers to work properly. Okay, there we have. Juan is still here. Nakia is still here. Roy's still here. Scott's still here. Thomas is still here. And I'm surprised Valerie's still here. Wow, okay. She's not playing hooky today. Okay. All right. Is that everybody who's still here? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep, I'm the 12th one. Okay. So we lost Bridget. That's all that we lost, I think. Let me go on and mark those who never showed up today. Patrick hasn't made it today. Parisha hasn't made it today so far. Harry hasn't made it today so far. Rod hasn't made it today so far. Jacob hasn't made it today so far. And Leon hasn't made it today so far. Okay. Now, do any of you have any questions about the lab? Okay. And again, what I'm going to do once we leave here, I've got to finish doing the test for the calculus class, but hopefully that won't take too much longer. Then I'll finish typing this lab. That will take a little bit longer, but not super much. And then I will finish working on the test for chapter 23. And I hope I'll get them all out there this evening sometime. So this is all that's required in the lab. Does anyone want me to go back so you can record what you need to record? What you need to record, I'll tell you. In each of these things, yes?
I was just going to ask, like, are all the previous labs recorded as well?
Yeah, as much as I could. Some of the labs y'all were working on your own, like the computer lab, rocks and minerals, you did those, but all the instructions are there. I mean, I got you started. I just didn't have a computer. I told you computer sites to go to, and I may have actually shown you how to get there, but then I didn't go through every mineral. Y'all did those on your own. But yeah.
Is this the last lab in test?
No, we'll have chapter 24 lab and tests on Wednesday. It's not going to take us long to finish chapter 24, and it won't take us long at all to do the lab for 24. And then I'll give you the test for 24 and the final exam. And actually, you probably would have, if you wanted to do it, finish it all in your 2 hours and, no, 3 hours and 45 minutes, you know, if you wanted to. You don't have to. You can check out whenever you want to. But I will, that will be after Wednesday. But because we have very little chapter 24 left to do, and then once we get that done, the lab is shorter than this lab, and then I think it is anyway, pretty much, and there may be more blanks to fill in, but they're pretty easy to fill in. And then the test, you can do that whenever you want to, but if you wanted to, you could probably get it done in the time we got left in class if you wanted to. I'm not going to be online answering your questions, because that's what the test is. You'd answer the question. But then the final exam, I think you'll find is very easy. It's matching. It's not even multiple choice. It's matching. Okay. Is there anything else in? Yes.
When is the last
we, we, uh, Wednesday is the last day we'll meet as a class, and we'll finish chapter 24 and do the lab and give you the test and the final, on Wednesday, and then you turn it in. Technically, the way they have it on the calendar, everybody does the final on Thursday, which is ridiculous because you have other classes on Thursday or you're at work on Thursday or something else. That's why I'm giving you the final on Wednesday, and you turn it in whenever you can get it in. Okay.
So when is the last day to submit all assignments?
As soon as you possibly can, because they've all been due already. Today is actually when the research paper was supposed to be in, but get it in as soon as you can. And then, the first labs and tests, they should have been done within a couple weeks of when I gave them to you. So, you remember I said I always give you a week to do it, but you can have longer if you need it. Well, that's way past time. So anytime you can get them in, get them in. Okay. Now, I said this earlier, and it may have been before you came in. Just because you don't see a grade on Blackboard doesn't mean I haven't gotten it yet. If you have received notification that I printed it, don't send it to me again. Okay. If I've emailed you back or sent you a message back and said, okay, I got this, I'll grade it when I can, and then I'll post the grade on Blackboard. A lot of those I have graded, I just haven't gotten to post on Blackboard. And for those who don't know, this is what I have left to grade. I had a stack about twice that big going into the weekend, and I got about half of them graded over the weekend. Large number from this class, but I'm up to chapter 19. I've got everything through chapter 19 graded, but anything that was turned in before Thursday. In this class, things that were turned in before I left on Friday morning, it's just this much right here. Okay, just a few left to do. I'm sure some of you turned in things over the weekend, so I haven't printed those yet because I was not anywhere close to a printer and had terrible internet all weekend long. So I'll be printing those once I finish the calculus test, today's lab, and today's test, or chapter 23 test. Then I will start printing again, and that's probably going to take me the rest of the night, is to catch up on my printing. Then once I get everything printed, then I'll be trying to catch up on my grading. Once I get everything graded, I'll be trying to catch up all of my Blackboard. So it's really piling up, sort of on y'all, but also on me for this term. I hate it that I had to go out of town, but we had to be there this past weekend. And like I said, I got most of your stuff that was turned in graded, and all of another class and parts of other classes, but I got most of yours done, but not all of it. So I'll be printing forever, grading forever, so get me stuff in as soon as you can, and once I print it, I'll acknowledge that I received it, then don't send it to me again. Otherwise, I'm printing the same stuff over and over, and that's just wasting time that I could be grading. Okay. So any other questions about today's lab? I'll be glad to go back and show you anything if you didn't get all those things recorded on those 3 periods. Say that again? Yeah, but it has to upload first, and it usually takes it's been about 2 hours recording, so it's going to take it pretty close to 2 hours to upload to YouTube, and then once it's in YouTube, I move it to the playlist, and once it's in the playlist, then you can access it. So it'll be probably a couple hours before it's there. Okay. Any other questions? Okay, you got a pretty good idea what to do? Does anyone want to see any of it again? I'll be glad to go back to any screen that's real easy to go to. And there will be about maybe around 30 questions on this lab. Well, there will be more blanks because one of those questions has 4 parts. So, yeah. Okay. I think it was about the same for all of them, but let's go back to, yeah, let's go back to 1750 and reset. Let me get, I don't know, can y'all see these names? I'll get those out of the way. Okay, and let me stop this. Okay, there it is. Well, it was about -8, -9, something like that. Valerie was right. And then it started dropping some. Wait, that's today, sorry. But I think it was about the same. Wait. 1750, I know. I'm sorry, I went to the wrong one. Okay, let's reset. Oh, I know. When I reset, it goes back to today. So I need to stop that and stop this. Okay. About minus, no, it's playing. Okay. It was about minus, let me try it again. Yeah, I know. Let me, 1750. Okay. Okay. Yeah, -8, -9, right in that range. And then I don't know why it drops to begin with, because it takes a while for the photons from the sunlight photons to come down. Then when it gets near the surface of the earth, that's when the infrared photons start showing up. That's what raises the temperature. The sunlight itself, believe it or not, doesn't. The sunlight has to shorten the wavelength, lengthen the wavelength, lower the frequency before it becomes infrared heat. So that's why you have to wait till you start getting infrared photons for the temperature to turn around. Okay, anything else? Good questions. Okay, Capri, I see your light's on, but I don't hear anything. Are you trying to say something? Maybe not. Okay. All right. You want me to stay on the air with this so you can ask questions, or you want me to get busy trying to get the form out there for you? Okay. I've got it all here, and you probably couldn't read my writing anyway. It'd probably take more for me to get you this information than it would take me to finish it. So I'll try to finish. Anyone else need anything before I close this down? Now, if you don't want to wait for the form, and if you got all the data down, you can send it to me. Or if this uploads to Blackboard, to YouTube, and you can access that before I get the lab finished, you can send me once you've seen this. Or if I get the form to you and you want to go onto the form, you can wait till that. But whatever floats your boat. I have a feeling most of you have plenty to work on. I'm guessing, right? Either research paper, old labs, old tests, or this new lab or new test, which is not out there yet. Okay? So you want to have any questions before I shut it down, or go on and shut it down? Any comment? Okay, if I don't hear any objection, I'll shut it down. Okay? I don't hear anything. Okay. I'll shut down this, shut down that. That's part of my calculus test. Don't tell anybody. Okay. Minimize that anyway. Okay. And I'll stop the sharing. I don't want to share anymore. So take care. We'll see you on Wednesday. Okay? Good deal. No last thoughts, parting shots? All right. I'm ending the meeting for everybody then. Bye-bye. We'll see you Wednesday.